present here. Christian Madel, Hervé Lamy, Karine Sautier et moi-même Laurence Roseau. Online, so Dusan Onic, who is one of the civic advisors, and Marco Stalewski and Vladimir Zekovic. So, Kristina Rackovic, we are going to listen to your presentation for about 45 minutes, and then you will ask questions.
Okay, thank you. I will put my timer because this is in PDF. I don't have timer on my presentation because it was impossible to share it like that. Okay. So today I will present my work, and my work is basically relying on the dust detection, in situ dust detection. What's
louder?
Okay. Outline of the thesis is actually at the beginning. I will say something about dust in general. After that, I will continue with my model that we developed during my thesis, and in the end, I will briefly present some interstellar dust detection. So actually, we should be happy because we don't have to dust in space because the universe is full of dust. And recently, we have some really beautiful plots obtained by GWST and from the deeper space. But we don't need to go so far away because we can observe dust also in the solar system. And for example, through the zodiacal light, which is actually the sunlight scattering by the dust grains, which is really nice because we can actually observe dust in situ. And in the solar system, two most prominent the dust populations are interplanetary dust and interstellar dust. So let's say a little bit more about dust grains. I mentioned that we have interplanetary dust in the solar system. So they're basically the parts of the comets and the asteroids. They're originating from the comets and the asteroids. And interstellar dust is entering the solar system from the interstellar medium. And here we can say that we can make one more assumption that dust grains are spherical and compact, and they have certain density, which is 2.5 grams per square centimeter. And on this base, we can assume some sizes and masses of the dust. And under this assumption, we have different dust populations. And in this particular thesis, we are dealing with the interstellar dust and beta meteorites, which are in the size range smaller than 10 to the minus 12 kilograms. Okay, how do we know all of this? Because for ages now, we were detecting dust in situ by some specialized dust detectors that were on the spacecrafts. And so during the time they evolved, but actually what was really interesting in the 1892 on Voyager crossing by the planet, they detect some really sharp signal, and with some analyzing, they realize that it's basically the dust detection. And this is the first time that the dust were detected with the radio instruments, which is actually really, which opened a completely new window in the investigation of dust. And okay, what happened here? If we have some satellite, we have the radio receiver, and the charging processes around this probe can be due to the plasma electrons, due to the photoelectrons, and so on. But one of the charging could be from the dust cloud that will be obtained after the influence of the grain itself. Also, what is important here to say, if we use radio receivers for dust detection, we should notice that there are two kinds of those receivers working in dipole mode, which basically is the measuring of potential difference of the potential between the antennas themselves and the monopole mode, which is measuring the potential between the spacecraft body and the antenna. And okay, here is some small sketch of what is happening with this charge around the spacecraft. So assuming that we have a positively charged spacecraft, and at the beginning, it will be in some equilibrium stage with some equilibrium potential. This is this green line. And at the moment when the impact occurs, there we will have some impact cloud generated. And in that impact cloud, we have free electrons and free ions. So since we have the positively charged spacecraft, we will the electrons will be attracted by the spacecraft, or a portion of them will manage to escape. And so this small blue is due to the escaped electrons. And after that, ions also will escape from the spacecraft. It's what we expect. And at one point, spacecraft will try to go back to the equilibrium. So this is the actually the qualitative model. It's what is to explain what is happening around the spacecraft. But what we wanted actually to do is to make some quantitative model, some mathematical model that can explain this process. What is also interesting here to point is this equation that is made in 70s, and that say that the total charge from the cloud actually depends on the mass and velocity of the impact of the dust grain, but also it depends on those three parameters which are connected with the geometry of the spacecraft, with the material of the spacecraft, and so on. So for each spacecraft, those parameters can vary. These values that I put here are some general average of the values, but for each spacecraft that can differ. So, okay, now we can talk about model, we can introduce it, and we can introduce some more maths in the problem. So, okay, now we think that we wanted to start with the spacecraft. In our case, we wanted to concentrate in the monopole observation mode. And here we have dust impact. We have basically the instrument that is making the voltage difference between the spacecraft and the antenna, and we will see this shape of signal. It's really characteristic shape for the dust signal, and so this axis is time. It can be it's usually in milliseconds, and it depends from the different spacecrafts. It's basically the time resolution of the instrument, and this is the signal amplitude. It's usually presented in millivolts. So what we wanted to do is is to model the potential of the spacecraft. So here we assume that we have the spacecraft in the monopole mode. We have system of the two elements. We consider that the one element is the spacecraft and the other element is the obtained cloud. And so each of those elements are defined by charge and potential. So here we wanted to model some elastance matrix that will connect those two components of the system. And so first, let's define this self-elastance component, which means that we don't expect that the capacitance of the spacecraft will be changed under the influence of the dust, because the size of the spacecraft is huge. So we expect that this self-elastance should be equal to the capacitance of the inverse of the capacitance of the spacecraft. Other component is mutual elastance between the spacecraft and the cloud. So it's obvious that it depends on the distance between the spacecraft and the cloud. And so it depends, of course, of the spacecraft capacitance, but also we need to define this F function that depends on the distance. It's okay, it's decreasing function because if the R is 0, the function value will be 1. Or if f going to infinity, we will have 0 value for the f. So we could choose basically anything for this f function, and we realized to use this exponential function. Okay, I don't know why it's not okay. And what we did is, from all of mentioned before, we obtained some equation of the potential perturbation. And this equation is nothing actually probably known to some people, because it's mentioned in the Zaslavsky paper from 2015. But he used just the left part of the equation, and he presented as the time variation of the spacecraft charge. So he actually tried to explain that all the charge that is happening is actually due to the electrons from the cloud. And so he defined this, I'm sorry, this charge that is happening by the influence of the photoelectron current about the solar wind current, and current of the electrons from the cloud. But what we wanted to do, we wanted to try to include also this electrostatic influence effect. And basically, this is the main goal of our work. And how we did it? Okay, since the previous equation was nonlinear, we wanted to linearize it somehow. And how we did it? Because we expect that this delta phi is really small comparing to the phi equilibrium. So we said that we expect those small potential perturbations, and we include it in our previous equation, and we obtain something like this. It's a linearized equation. And here we included new term, this tau spacecraft, which is actually relaxation time of the spacecraft potential. If you remember that small sketch from the beginning, actually this is the time that the spacecraft will need to go to the equilibrium. And of course, it depends on the environment and of the capacitance and geometry of the spacecraft. Okay. And so this, we wanted to find some general solution of this equation. So we suppose that spacecraft is in equilibrium with the surrounding plasma, so time is going to the minus infinity. And anyhow, here it's important to say that we have those two parts that are really important to solve in order to solve the equation, basically. And first, this I collected is actually the effect of the collection of the electrons from the cloud. And the second part is effect of the influence of the ions from the cloud. And in order to make it easier to solve, we assumed two things. We assumed that electrons from the cloud are massless, and they actually are streaming really fast, instantaneously. So whatever happens with the electron from the cloud, it should be instantaneously. Either they will be attracted, either the part will manage to escape. All that process is supposed to be instantaneously. And for the ions from the cloud, we assume that ions are streaming from the cloud further away with the constant velocity. So we said that it depends on the distance, and so this is the spacecraft ion cloud distance, and we expect that this velocity should be constant. And so regarding that part of the previous equation, we now have this term that ion cloud dynamic time scale. Actually, this is the time scale of the propagation of the ion cloud. And if we include all of this in our first assumption, we will obtain something like this. And we will have here, okay, this epsilon is the amount of charge that managed to of electrons that managed to escape. This Q is total charge. We have spacecraft capacitance and ion time scale and spacecraft time scale, or that we already mentioned. If we make some assumptions on this, and if we put that, let's say, those values for those parameters, and we need to normalize the pulse with minus Q and capacitance of the spacecraft inverse of the capacitance of the spacecraft, we will obtain some really nice curve that is basically really look alike what we could see in the data. And this zoomed part is interesting to explain, because here this really steep part is during the fact that we neglect the time scale for the electrons. And since we had the model, we wanted to find a way to test it on the real data. And the decision was to do it on the stereo. And so, okay, stereo is orbiting and at 1 EU. We had there are 3 orthogonal 6 meters long antennas, and it's working in the monopole mode, which is really good for our model. And so we can use the time domain sampler, the data from time domain sampler that are actually snapshot with resolution of 4 milliseconds or 8 milliseconds. When you look into the electric signal data from the both stereo satellites, you can see something like this. Those are some examples. It's a lot of different things that you can find inside. But one of the snapshots is related to the dust, and so but we were interested just in those events. So we had to find a way to distinguish those events from the whole database. And how we did it? We had to make some assumptions. Okay, we said that we are interested just in events that are measured by all 3 monopoles almost simultaneously, with in the range, with the amplitudes in some range. We put a range for the amplitudes between 15 millivolts and 175 millivolts. There is a reason, because 175 is the threshold for the saturation of the instrument, and if we have saturated event, we cannot use it. And for the 50 millivolts, we wanted to have spike large enough to be noticeable by eye. And so here is the example that it's presentation in 2D. So I put this Vx antenna, amplitudes from Vx antenna and from Vy antenna. And here in red are actually those red spots, or I think, yeah, they are what we are looking for. So they are data that are measured, events that are measured by both antennas and at the same time almost. So in 3D, we decided that they should be probably in some kind of cone, and we defined the aperture of the cone, it's 70 degrees. And once we obtained this, we wanted to test the algorithm. And actually, we realized that sometimes we can find also long mirror waves in our database. In order to remove them from the database, we used the crossing rule. Actually, on 1/3 of the amplitude, we said if there is more than 2 crossing points, this is probably not dust, and we will not use this event. And so we applied this algorithm to all database from the stereo A and stereo B, and what we obtain is around more than 150,000 events. And since they're triple hits, so it's ×3 signals actually, because we have the signal for each antenna. What is also here, what also happened, oh my God. This is that, okay, for the signal, we expected to see that the beautiful one that we actually present with our mathematical equation, but it was not really like that in the reality. And which is okay, because since we have basically we are measuring the difference between the voltage of the spacecraft and of the antenna, and actually we are measuring the difference in the voltage between 2 spots, but between those 2 spots there is the chain of electric things, and so it's to expect that they will somehow affect the signal. So we were not sure this overshoot that we can see on some signal plots Is it related to this electronics problem or signature, or is it something else? So we used inverse transfer function that is obtained by the engineers from Lesia, and we multiplied the RAV signal with this transfer function. We then applied the FFT, again, inverse FFT. And so we had, what we obtained is that deconvolved signal. So we consider that we deconvolved signal from this electronics effect. Sometimes we are really happy with the results because the overshoot will disappear, but sometimes it remains. So maybe it's not always just due to the electronics, but can be also due to the fact that actually antenna will take some charge from the cloud. But for now, what we did, we prepared our also with this deconvolving, we prepared our data for the further work. And what is it? We actually wanted to fit our model to the real data. We use this function. And so here you can see those are 4 free parameters that I mentioned before. But this, okay, let's start with this A. It's actually total charge. So it's from here to here value. And the B should be just this part here. It's the overshoot. Sometimes we can have events without overshoot, as this example. And so ion time is basically the time, this part of, and the relaxation time is actually this. And what we see here is that basically fitting works properly, except for those events where with the prominent overshoot, but since we didn't take it to account, it's okay. And so we will see what we can obtain from the results. So we have 4 free parameters, and the first one is a relaxation time scale. And since we defined this time scale roughly with this equation, we can estimate the value that we expect for stereo, and it's between 0.1 and 0.43 milliseconds. And actually 80% of the data fit in that expected range. So it makes us to believe that our work is good, the model is working properly. So we skip to the other parameter, which is the ion dynamics time scale. And so, okay, again, we expect that ion time scale should be smaller than the time scale of the spacecraft, and so it should be smaller than 100 microseconds. And actually, again, 80% of our events are in this range, so we should be satisfied. And also, here we could use those values that we obtain to estimate the speed of the propagating ions. So we use this equation that was described first time in the Meyer-Werner paper from 2017. And so assuming that the spacecraft photoelectron current density is around the 20 micro, and this is the total charge. That is this is the typical value, the medium value for the total charge that we obtain, and this tau e is basically this value here. And what we obtain is that the speed is around 13 kilometers per second. And which was really interesting because it was in the agreement with the experimental values from 2012 that they said that it should be larger than 10 kilometers per second. So this is actually the first time that this value is obtained from the real data, which is a really interesting result. What is also interesting result is that, okay, we realize that electrons sometimes manage to escape. Here we can see that this is the total charge and this is escaped charge. And so we were curious to see what is the amount of the charge that will escape. And so, since I already mentioned that there is always this pre-shoot, we put some threshold. We say, okay, if there is the pre-shoot larger than 5 millivolts, we consider it as a real pre-shoot, and we will distinguish just those events. And in our database, there are 20% of such events. So looking in just those events, we realized that actually around 8% of the charge escaped the spacecraft, managed to escape the spacecraft. Knowing this and assuming the Maxwellian distribution of the temperature, it is possible to estimate the temperature of the impact-produced electrons. So we can use this value, and this epsilon, it's 0.08. We know that the Phi spacecraft is 5 volts, so we can estimate this T is 2.7 electron volts. And again, this is interesting because comparing to the model that is to the experimental values, it's really look like that we obtain something nice. And so to summarize this part, we can say that we obtained the interesting analytical model that takes into account the electrostatic influence effect, which is the first time ever that something like that was done. And we validate our model using stereo data. We realize that really model is adaptive to the huge database. And from those data, we obtained some interesting results regarding the propagation of the speed of the ion from the cloud, and also to the escape current. What remained as the open question? This overshoot, we are not completely sure what is behind that, and so maybe it could be interesting to try to include this charge collection by the antenna and to see what's happening. But for now, we were satisfied. And what we wanted to do next, we wanted to test our model to some other database, and actually the special one, which leads us to the other story, and it is about interstellar dust. So what's happened actually? When we were working on our model, the solar orbiter was launched. It was in 2020. Everybody was so super happy. And okay, also the dust people, because it's equipped with the 3 antennas, 6.5 meters long. And it's also they have the TDS system that produces the data in monopole and dipole mode. So we expected that we will detect some dust, and furthermore, that we can test our model. And indeed, we did detect some dust in the first encounter from the April 1st, 2020. There is some interesting dust detected, and so here is on this time, and so impact rate per day, and this is representing the distance from between the spacecraft and the sun, and so anti-correlation between the flux and the distance to the sun tell us that we are observing particles with some radial velocity, which is okay. We expected to observe some beta meteorites, so we are satisfied with that. But what was strange, that we didn't see any modulation of the observed dust in the aphelion at 1 AU. And we expect it because we, considering the stereo data, we knew that, for example, in 2012, it was the component of the interstellar dust. So we were curious what's happened and why we don't see that component. And okay, what we know for dust, for interstellar dust so far, we are sure that in the solar system there is some interstellar dust flow. It was measured by Ulysses, and after that it was also on Helios and Cassini. And information that we have about interstellar dust flow, that it's the ecliptic longitude and latitude, and also we know that it's entering the solar system with the speed of 26 kilometers per second. What we also know that we already could see it on the stereo and wind. So we have the papers actually from 2012 and 2014 that deal with this phenomena. So we expected to see it, as I said, on solar orbiter. And so, but we don't know, maybe that something changed now also on those probes. So we decided to go back to the data and to revisit basically the data and see what's happening those days. And what we did, we started with wind. So here we have wind satellite that it's launched in 1994, and so we have 3 orthogonal antenna, but the operating mode is monopole. It's a little bit complicated, but we don't want to go into the details. We just want to see what's happening with the dust flux over years. And so we can see here, at the beginning, the wind is in the magnetosphere of the Earth, so we don't expect to see a lot of dust. But after, we have seen some random fluctuations here. And at one point, those fluctuations actually become really periodic modulations, like in this period. And again, after that, they stop to be periodic. And then again, we have some random things. And since we have 24 years of data here, this we could expect some long-term evaluation of the heliosphere due to the solar cycle. So we went to see a little bit about solar cycle. And so if we assume that solar cycle is 11 years long, and that at the beginning we have the solar minimum with almost parallel solar magnetic lines, and that during the time those magnetic lines become more and more complicated. At some point that they are really complex, and so we will be at the solar maximum. It will be a lot of solar activity, and at one point this magnetic field will be so complicated that it will flip and change the polarity, and after that it's again go to the minimal phase, and so on and so on. So this process of basically of flipping is 11 years old. So we wanted to see, since we have the basically 23rd and the 24th solar cycle for wind, maybe is it correlated to what we can see in the data. So we put more details on the previous photo, and actually what we did, we colored the years that are in the minimum phase with this yellow. I hope that it's okay. It's nice. And so this is the minimum phase. Then it will be exceeding phase that everything become more complicated, and after that it will be the maximum phase, and in the end declining phase, and it's 11 years. And again we will have the same cycle. And what we can see actually that the period with those nice modulations is actually during this almost minimum, and during when the solar magnetic lines are pointing southward. And again, what was strange that the other minimum, during the other minimum, we don't have those modulations. And but what is different is that the solar magnetic lines are pointing northward. So we checked the same thing on the stereo A and stereo B. So here, stereo A starts with this phase where the magnetic field lines pointing southward. And so we see some nice modulations. And after that, here is the gap in the data, but still after that, there are no modulations or some random. And for stereo B, unfortunately, we have just the data till 2015. After that, we lost the connection with the satellite, but still some nice modulations can be seen here also from the stereo B until, after that, we don't have. And so actually those modulations should be considered as the orbital modulations. And why? Since, if we assume that we have the sun in the middle here, and this blue circle is actually the trajectory of the spacecraft, we can say that interstellar dust is entering from let's say this direction. So we will have this component of the velocity of the interstellar dust. We have, of course, velocity of the spacecraft, and we have the velocity of beta meteorites. So it's it's typical to expect that at this point, at one point, when the spacecraft and interstellar velocities are parallel, that we will obtain less interstellar dust flux than in the opposite when they're anti-parallel. And so we make we used some simple equation for that. So this is the rate of the flux, so the dust number density and the velocity of the impact, and the impact velocity is the difference between spacecraft and dust velocity. And so this is the expected impact rate. So we consider the component for the beta meteoroids, and we consider component for interstellar dust. And what is here to point is that okay, we know that the longitude and the latitude of the interstellar dust. So we wanted to use this simple equation, and to using its least square fitting function with this equation, we wanted to apply it on the real data. And what we did, actually, we took the part when there is a solar minimum and where the solar magnetic lines are pointing southward. And so this is for the period between 2007 and 2011. So this is the longitude, and this is the flux in per square meters per second. So this is the median value between those for those 3 years. And what we can see, this blue is actually the fitting line. We can see that there is some modulation here. And so, okay, I forgot to say it here that we have those fixed parameters. We put the values for the spacecraft, for the speed of the spacecraft, for the interstellar dust. I said it at the beginning that it's 26 kilometers per second, and for the beta meteorites. And also we consider the latitude for the interstellar, and we had to put some value for the surface of the spacecraft because it's important. It's mentioned in the equation. And for we did the same for stereo A and B, but in the same period for the same years basically. And what we obtained from the results. So we obtained some interstellar dust flux. This is presented here. So it's for wind for stereo A and stereo B. And we obtained the values also for the longitude of the interstellar dust flow. And so the things that we obtained, actually the values that we obtained are matching with the one that are previously published in the paper from 2012 and 2014. And so we were curious to see what will happen in the data, but for the period where we also have the minimum, but the different polarity of the solar magnetic field. And so we took the period from 2016 until 2020, did basically the same procedure, but it's obvious here that okay, you don't see it's quite flat, this flux. There is no some prominent modulation that we can see, and also with the results that the interstellar dust component is significantly reduced. And so furthermore, we wanted to see what's happening from year to year. So we estimated this interstellar dust flux annually, year by year. And so for wind, you can see here this yellow part is for that minimum phase with the solar magnetic lines pointing southward. And so you can see that before the flux is around 1, and so a little bit higher after. But in this period, it's significantly larger. Also, it's this is for this period because it's the different time scale. We don't have we have the stereo data just from 2007. So here again, you can see that at the beginning of the stereo mission, when with the same conditions as here, we had the pretty high interstellar dust flux, and after that it's going down. And so this is also just the beginning of our work. This is the work in progress, but still what we can see from all of this is that on all three spacecraft we can see those basically orbital modulation, but that they are really connected to the special conditions of the magnetic field and to the minimum of the solar cycle. And so according to this, we can probably say that if the next flip of the solar magnetic is in 2025, we probably should expect more interstellar dust in 2028. But really, this is something that can be really interesting to go into the further or deeper. Anyhow, here I will stop with presenting my scientific results and just make some short general summary. So we have new model as a product of the work on the thesis that takes into account electrostatic influence effect. We made some auto detection algorithm for the dust on the stereo, and we managed to monitor interstellar dust flux at 1U by different spacecraft on a large time scale that can be really useful for the further work. And what are perspectives? As I mentioned, for the work on the model, it is we would really like to use our model to analyze solar orbiter data. Also, it would be interesting to upgrade the model with the electrostatic influence of the ions cloud on the antenna. And why not? We can test our model also on Parker Solar Probe data. It could be interesting to see the results. And regarding the interstellar dust, it would be nice because the model that we use is very simple. It would be nice to maybe make some more complicated model to distinguish more precisely the interstellar dust flux, as also the longitude value of the interstellar dust flow, because there are some assumptions that it's changing with time by, I think, by 1 degree every 5 years or so on. But it would be really interesting because we have this long time scale to see what can we learn from it. And also, I didn't use this spacecraft velocity, and it would be interesting because it's definitely it depends on the spacecraft velocity. So maybe we can also take it into consideration. And extra, what can be interesting to do is basically we have two really huge databases of the dust. One's from stereo A and B, and one is from wind. And maybe that can be used together to make some machine learning routine that will help us in the future to distinguish dust easily from other probes. Thank you.
So we are going to do questions. Can you hear us online?
Oh, yes.
There's one message in the So we begin with the questions of the oratory.
Okay. So first of all, thank you very much for this nice presentation, this nice work, a lot of data analysis and a nice model. And I must say, I was actually happy to go back into this field because I worked a long time ago now with the people here in the Don and Karim and others. So it was actually nice to be back again for this field and this interesting physics. Okay, I think I understood most of the physics that we explained in the document and today. still I have a couple of questions that I would like to mention. So you studied 20%. No, you mentioned that you have these precursor events.
Yeah.
In approximately 20% of the cases.
Yes.
Does that mean that in the others you don't have them, or they are too low to measure?
No, you can measure them, but they are lower than 5 millivolts. Their amplitude, because I put that threshold for them, is 5 millivolts. And if the value is smaller, I don't consider them as a pre-shoot. And so, but it's okay if we assume that they depend actually on the speed of the grain. You know, if we have a more faster grain, we will have more charge of the cloud, and so it means that the parts, it's more realistic that part of the electrons will manage to escape the portion.
Yes, so it could be that when we don't detect it, that actually electrons.
Yeah. We don't expect them that they're not obliged to leave the
I had a question about the overshoot. You actually mentioned it in the perspective of this work. So basically, this left overshoot that you still have after the evolution, it could be due, if I understand well, to the antenna. That in this case, you assume that the potential is not modified by the impact.
Yeah.
So if you have to include it, you would have then 3 equations, right?
Actually, I need to extend this one and to include, actually, now I have 2 times 2 this matrix, elastance matrix, and I will have to include, if I want to include one more member of it, so it will be 3 times 3. So I need to include the elastance matrix between also the cloud and the spacecraft, and the cloud and the antenna and spacecraft, and so on. So it will be probably more complicated.
And yeah, my question then was: is there a possibility to still get an analytical model, or do you have to invert this?
I hope it is, but I honestly didn't try, because at the beginning we just wanted to see, is this model working properly? And the idea was really to test it on the solar orbiter data. And so at the beginning of the mission, we expected the same conditions at 1 AU as for stereo. So after that, it was like it was the idea to involve with model involving with the data from stereo, so from solar orbiter. So we didn't actually. We were thinking about that, we were considering it, but we didn't work really on it.
And just to be sure, the idea that in most cases the potential of the antenna does not change, or at least significantly.
In the monopole mode, in most cases, it's not changing.
And
yeah.
it's due to the
Yeah.
surface, right?
Yeah.
Sorry, my question, but yes, so yeah, in the document you also mentioned potential applications that you did not discuss during the presentation. Here is about this magnetic pulses.
Oh yes, but that's also that is some roughly assumption that since we assume that whatever happens with the electrons it's attenuously, so it means that the instrument we have 4 milliseconds is the minimum of the time scale of the instrument. So if we have the instrument with the better time resolution, we could probably measure something. And so the idea was actually that we connect we need a lot of charge, as I told you, it should be a bigger charge if we want some portion of the electrons that escape. And so the idea is, because in the solar orbiter data, they see something that they think that it's due to the dust. And so it is to expect that those events should be basically saturated events. because it's too large to be measured by the signal. So we can assume that escaped electron current, but for that we need to define some value for the tau electron. Yeah, we need to time scale for the electron, and it is definitely smaller than 4 milliseconds, because on stereo I checked it, and basically we never see that
So we're talking about the rise time of the.
yeah, but we're talking actually about this. Oh, there is. Okay, this, yeah. So if we had some time scale for the electrons, this wouldn't be so sharp. So we will hear some curve here, but small anyhow. And after, so we will be able to calculate this time scale for the electrons. And that's why I mentioned it when I was talking about this, that this is really why it's so sharp, because in our model we consider that it's 0.
Yeah. And for the second part, yes, I think you mentioned it in the document. Then that because of course because along the trajectory, so depending on the solar longitude, you will get different speeds for the interstellar dust, and therefore you will detect different masses.
Yes.
Mass range. And so how would that impact the conclusions and the speed?
We can probably obtain more precise values for the interstellar dust flux, but it shouldn't differ much than this, because I don't want to say that interstellar dust disappear. We can detect it also, but those small grains are not going to reach 1 AU in such conditions. So we can extend probably the model with some differences in the masses. It will obtain us more precise results, but definitely in the data, it's what we see. There is no that orbital modulation that it should be that.
Okay. And if I may have one comment, is also that the sketch that you presented at the beginning, slide 6, I think, was actually would have been very, yes,
Okay.
It's actually really nice, and would have been interesting to include it also in the document, because it's very visual. And
yeah, it's really great. It's from Ingrid's Mann paper 2019. Okay, she put some. Okay, I put it. Yeah. And so it's she also took the different situation when the spacecraft is charged negatively, but we are not interested here because we expect so stereo is definitely positively charged.
Okay, and maybe a last question, yes, because I see the formula there. So this empirical formula relating based on experiments relating the charge and the mass and the speed. So it obviously depends on the material.
Yes.
So that has been done for the material used for stereo, I think.
Yeah.
And what is the typical mass speed range actually that is used? I mean, can you easily? I know you have to make assumption, of course, but can you easily?
I think it's between 50 and 80 kilometers per second. Yeah, I think it should be as far as I remember, it should be larger than 10 kilometers per second to actually obtain any signal. But basically, for those triple hits, it's between the 50 and 80.
So it covers all the speed range of the.
Mm.
Yeah, probably not. Thank you.
Thank you.
Okay, so first of all, thank you for this nice presentation, and I'm also very happy to come back to this topic because it happened that I was the member of the jury of Soraya Belwan 10 years ago in London on the work of nanodust. And I'm not a specialist of this domain. I'm very happy to come back to this very interesting field. And meanwhile, I've seen some observations and some work, especially from since you are working in a team who have a very high reputation on this topic, and it was well known worldwide about this very interesting scientific questions. And your work is really a continuation of the previous work that you have mentioned. And I really have appreciated during your presentation the way you have shown what you added to the previous approaches, by Arnaud, from Nicole, in the past, and so on. And I really appreciated that because that's something I already discussed about your document that is extremely important. And so for me, I must say I'm a person, everybody knows I'm from Ira, so I am a particle person. I'm a particle spectrometer person. So that's something which is very, very far, but we are, the commonality is really the spacecraft potential, which for us is a big issue, especially when you have an electron spectrometer, and the one who is working on Mars now, the MAVEN mission. In fact, I come back to MAVEN because your topic is really ubiquitous, because these dust impacts are everywhere. And there was observation made by MAVEN from the London probe, the LPWS instrument published by Lyra Anderson in 2015. And this is mentioned in the nice review by Ingrid Mann you mentioned here. And she has put all the environment when this kind of observation can be made. And as you really said, it's nearly 40 years ago. That was a good illustration of serendipity, because the instruments which were not designed for studying something were able to produce very nice and interesting physics about that. Okay, so I said I really appreciated also the document manuscript. I told you that I would like some small changes, very few changes, and especially we mentioned the same reserve about some figures which are in your publication in the appendix that are not in the text. And for the reader, it's really difficult. You have to jump from one part of the text to the end to find where is figure 2 of the paper, where is figure 3. But that's not that's only technical. Nothing that's very easy to change. So I have, of course, some questions, maybe too many. In fact, there is one. I jump on this slide. That's not your work, but about this expression on the right. I guess it comes from a lot of accumulation of empirical determination,
Yes.
as you said, from different all these parameters. That's the general view, and that's something which is because you give these parameters, but there is not so much error bars on these parameters and so much large range. Or in other words, it's relatively easy to come back to. I think people interested in the dust themselves. They want to know about the mass distribution, something like that. That's not your topic, but from your work, it's possible to go from the left.
Yes,
side of the
yes,
equation
yes,
and
yes.
derive the.
And for example, for stereo, there are values for stereo of the parameters. As far as alpha is 1, beta is 407, as far as I think, and I think this sigma is 1.2 or something like that. And so it's really the experiment. It's published by Colette, I think, 2014, and he did some experiments on stereo, on the materials as for stereo. So when I use it, actually, it's in my work. I use this equation and to estimate some things. So if this is basically it's really good defined for example for stereo, for materials such as stereo.
So there are laboratory experiments.
Yes.
I think the last in the laboratory in the University of Boulder.
Yes.
experiment?
They also, yes, they did a lot of different experiments, and actually those results are super useful.
Okay. So I come back. Yeah, I have a first very naive question, very basic question at the beginning, and I think that's very easy to answer, and this has been probably addressed already. You mentioned in your auto detection technique, your machine learning technique that you think.
Oh, but it's not machine. This is what I did. Is not machine
It's
learning.
not machine learning.
No.
There is a paper at the end.
Yes.
Also
Yes.
That's a different thing.
Yeah. This is different, and this paper is related to solar orbiter population. Yeah.
No, what I meant that you mentioned on your waves, you mentioned this kind of other disturbances.
Okay.
No, could you come back to this one?
This one? Okay.
And my question is that I'm also strongly involved in the shock physics and shock physics, and people in the shock physics they have shown recently in MNS data that there are some kind of electrostatic oscillatory waves,
Okay.
which are also short pulses, very transient events. How can you discriminate? Is it easy, or it has been already shown to be clear that you can clearly eliminate this kind of disturbances because they do not pollute your sample, or is it easy to get rid of them?
Actually, what I didn't think about each particular signal that I'm not interested in. I was just concentrated on those sharp spikes related to dust. And so basically what I did, I took 3 months of data and I put some conditions, and I tried to see what makes a difference. And I was by my eyes, I was checking. Is it working properly? Can I detect something else despite dust and so on? And only thing that I could find in the data after some time, let's say, trying to improve the algorithm, it was long mirror waves. Actually, because they can be with this really spikes, and they can go inside this range of the signal range amplitude, and so that's why I had to put that additional condition that I wanted to check that crossing, because in that case I'm sure that those dusts are usually really prominent, and so at the 1/3 of the amplitude there should not be something around.
No, I mean, this kind of electrostatic oscillatory waves are observed at shocks. So there must be an interplanetary shock.
Yeah.
I guess when you look carefully to what you observe, that must be very different, especially the waveform is not the same, but it has similar time scales and in time series and amplitude. So I'm just naively asking, is that being addressed?
No. I never saw it actually, and I had few. Okay.
Working in that, and when you look to the waveform, very quickly, it can be seen. When you look more carefully, it's very different from this. I agree with you. So you said by eye, you can really completely eliminate what is not what you are trying to.
Yeah.
Okay. So that's clear. Yeah, I have another question about the ion velocity from the cloud produced by the impact. You mentioned, I don't remember the slide, but you mentioned that it was, you assume, that it's very consistent with what is observed. You assume a constant velocity, that means you assume that the ion produced in the clouds keep their velocity, their initial velocity obtained in very regional processes at the impact.
Yeah,
and they freely escape.
It should freely escape, but it's
because just as a physical question, there are transients in the electric potential, electric field is varying with time. That means magnetic field is varying with time. That means electromagnetic forces could act on these ions. Is the argument that the time scale is so short that it can be completely negligible to consider any influence of these electromagnetic forces, and that considering a constant scale. Is that just again a question I have in mind?
Okay, we expect them actually because at one point when electrons just go wherever, we will have just the ion cloud basically, and we expect that this cloud will expand with time. And also what will affect that cloud will be electrons, photoelectrons that are actually in the sheet around the spacecraft. And so basically, if they want to escape, they need to have the speed larger than these photoelectrons, the one of the photoelectrons. So that's what we consider here, is that basically that this speed of ions is, let's assume that it's constant, but it should be larger than the speed from the, yeah.
I mean, the fact that it doesn't vary, it just can be a reasonable assumption.
Yeah.
The time scale, I think that's the argument, because the electric field and magnetic field are there, and the electromagnetic forces will act on ions. That's whatever they are produced by the cloud or incident, they will accept it's before the relaxation time that all these processes are occurring so much time scale. I don't know if anybody has addressed this question quantitatively, and that can be very easy, and at least it seems to be a very good assumption and nice result that you get. Okay, so I have another question, but I think Henri has already asked them about one point that you suppose that the potential of the antennas are keeping constant because you are looking only to the monopole, this monopole approach.
Yes.
And for if you have a dipole approach, it would be much more complex. Right?
Yeah, we cannot expect that, because in the dipole you actually there is the difference in the voltage between the antennas, and so it's much amplitude is much smaller, and so it depends a lot on the position of the grain, because it's not the same, is it close to the antenna or not, and so on. That's why this monopole mode is really good for dust observation, because you don't really care where the impact happened, because the potential, the capacitance of the spacecraft is large.
You assume that the impact happens on the spacecraft.
On the spacecraft, yeah.
Because it's just a reasonable agreement.
According to the size.
It's the big size of
yes.
the body of the spacecraft. But you mentioned in your text that some antennas were broken.
Oh, that's for wind. Yeah.
So the probability is much less.
It can happen for sure, yes, and but basically that's those situations like that with wind are the reason why the scientists started to study dust, because they wanted to keep improving the materials of the spacecraft, to protect the instruments actually. But yes, for the wind, I think it was 2000 and 2002, and it's the X antenna. At the beginning it was 100 meters long. And after that, after those two cuts, I think it's 25 or something like that. So it's really like, yeah.
And I jumped on another question about that. We already discussed that before, but there is no possibility to when you assume in this monopole approach that the impact occurs somewhere on the spectrum body. There is no way to imagine it is closer to the, if it is close to the point, to the part of the starting point of the antenna. Will there be a different signal in the antenna or compared to the other antennas?
Probably yes. Probably yes. Yeah, but we didn't. In that case, you need to take into account the antenna potential and so on. So that is again another step of the. So that's why we assume that it's no matter, but still I think that we discussed it. I am looking for the events that are measured simultaneously with the approximately the same amplitude, but it's never the same. So it can be also considered the position. Yeah.
What was the number? I remember on the single paper that there is there is there are cases where one antenna sees a much higher signal than the two others.
Yes.
That means that's the case of the impact on the
Yeah,
antenna.
that should be the case of the impact. And there also I put some strange examples of that in my manuscript, that sometimes you have some invert signal on one antenna, and all those complex situations, we didn't take them into account because I think there are 2% of such events in this huge database, so it's okay. But it can be also interesting to see what is happening behind.
Slash for future investigations.
Okay.
Okay, so I have, I don't want to keep too much time, but I have another question about slide 18, not this one. I think, yeah, it's about the cone. I'm still confused when I see this. So I think I understand now what it means. But my first question was, where is the cone? Where is the cone here, and why 17 degrees and not 20 or?
Oh, because it was like as I told you at the beginning, I was when I started to make this algorithm, I was just checking what are the results, and basically taking a larger and smaller aperture to see how many events will be inside that cone. And so this 17, it sounds silly, but it's actually it's 95%.
You mean you are dealing with you're not in the space, you're in space of amplitude, voltage
amplitude. Yeah.
X, V, Y, Z. In
So,
this space, you have a cloud of data points.
Yes.
You have a solid angle.
Yes.
And you consider the axis. And
Yes.
you try to be
as close as possible to that axis.
So you take what you. That is relatively similar because on this projection in VX, VY, we see some kind of code like the aperture seems to be.
Okay, maybe it was better to make, but I wanted to make it as easy as simple as possible, and obviously it's worse.
Yeah, what I mean that this axis would be the major axis of the ellipse.
Yeah.
And that's where the.
Like this.
Of course. Ideally, points should be there.
All of them, yeah. But it's never like that, and so we need to.
Okay. So that's clear because I think I told you it was for me at least it was not so clear in the manuscript. And I think I really agree. You should add a small paragraph to better explain that because then that's very clear. That's
okay.
In your procedure. I just want to. Yeah, I have a question. I don't remember on slide 23. Yeah, you mentioned regarding the. I think it was relatively clear what you did in the electron state. I just wanted to ask you compared to the approach that Michel Chen is using.
Yes.
I think he's using a kind of Boltzmann like that.
Honestly, I don't remember. Honestly, I really don't remember.
My question, how does it compare to your model? You have a little different approach?
He actually took into account the charge that is taken by the antennas, as far as I remember. Yeah. And he wanted to. Oh my God, I'm not sure.
I don't want to discuss this work.
Yeah, but
the advantages or why did you make different choices?
Actually, we never met, and I think after 2 years of my and his work, we realized that we are working on the same topic basically, but it was in the middle of Corona and on Zoom and so on. And so he actually his model is not analytical. It's not really easy to apply. And he tried actually to explain those complicated things. And I think that his idea was really to explain just some particular shapes. And our idea was actually to make it as simple as possible, and to make analytical model, and to make it easy to apply to I don't know, thousands of data, obviously.
Yeah, because you want a practical analytical model to simplify the data, and you can study the specific cases.
Yes, and I think that he did some simulations.
That's the way science is made. And I have a question now about, we come to the last, about interstellar dust. On your slide, I think 31 or 32, I'm close to the end. There's a president looking at me. You said you see no modulation on the right here. Maybe that's my own eyes. But when I look between 2016 and 2020, it's not really as nice as as in the middle of the plot. There seems to be some remaining small modulation. You said there is no modulation at all?
No, it's not periodical modulation as the one we can see here.
Yeah, here
and
not very
yeah,
obvious. I think it seems to be between 16 and 2020. We see at least something like 4 pseudo periodic.
Yeah, but when I plot it here, you can see it's quite flat.
Yeah,
Okay, there is something. That's why I don't expect that we don't see any interstellar dust flux, but we expect to see less, and it's significantly less.
Yeah, okay. So you can get okay, and I think I have a question about the magnetic field. Have you also asked it already? And the last question, you mentioned that from the beginning, and that will be easy to answer. What about the case where the spectral potential is negative, like when you are around the planet? I'm thinking about my topic in the hemisphere of Mars. There are dust impacts, and I guess the approach should be
completely opposite. Yeah, we don't expect them to.
Do that now.
Yeah.
So okay, thank you.
Thank you.
So we move the Maria online. Marco Stalewski. Do you have
Hello, can you hear me well?
Yes.
Yes, okay, good. Okay, I would like to thank Kristina for a very clear presentation and well-written thesis. I studied dust, but in a very different environment, in active galactic nuclei, so this is all very new to me, and I could learn a lot from all of this. So my questions are going to be rather basic, so I would first ask Kristina if you can elaborate a bit more on your future plans. Where do you see the most room for improvement? Would you like to improve the model, or you would go to applying your model to some other data sets?
First, I would like to actually apply it on the solar orbiter dataset, because I think that we can obtain some interesting results also. But also that can be the way to improve the model, because we have 2 different ways of data collection in on working on the radio instrument on solar orbiter. So we have the monopole data and the dipole data, and so that can be also some kind of way to improve to see how our model is working on those data. But there is a slight problem with the solar orbiter data, because we don't still have proper calibration, and in that sense, the data that we can, the information that we can obtain from those data are really not reliable. You know, we cannot trust to the amplitudes, to the time scales, and so on at this point. But probably very soon we will have some proper calibration for the data, and after that, I think that probably for those dipole, for those monopole data at least, it will be straightforward and maybe we will be able to find something very interesting. Who knows?
And about that overshoot issue, or how could you improve the model to account for that? You briefly mentioned it during the presentation.
Sorry, once again, I didn't understand properly.
The overshoot in the signal.
Oh yeah, that is actually that would be really interesting to include. It means that we need to include the antenna in our model, definitely, and it will probably not be easy, but once it's done, it will probably be really nice, because this overshoot is really the question mark. What is behind it? Maybe we are wrong. Maybe it's not due to the antenna is taking some parts of the charge from the cloud. Maybe we are wrong, but we will not. We will know that once we obtain the model that can approve or disapprove this theory.
Okay, and then if I understood well, the very first detection with Voyager, it was completely accidental, right? They saw some signal and then they figured out, okay, it must be the impact of dust particles, correct?
Yeah, but actually it was really serendipitous for this, but it was a flyby to the planet, so it's the dust around the planets, but actually the pioneer for the interplanetary dust detection is stereo. So that's why we wanted to use it's really definitely it's proved like a good probe to study dust on the data.
Yes, because I was actually wondering, because all the probes you mentioned, they were meant to study the sun, so solar probes, but I was wondering, so in principle, any spacecraft can be used for this, right? The entire body of the spacecraft impact surface and it just needs antenna, which any spacecraft has. So for example, could you use the same method to study dust particles at different altitudes in Earth orbit just by using data from different satellites there? Or for example, what about James Webb, which is in Lagrange point? Is there any obstacle of using those satellites as well?
Yeah, they actually I presented a few really nice pictures. I think that they're dust observations in infrared, so you basically can observe dust also with in different scales. But yes, the answer is, if you have the satellite with the radio instrument, basically it is to expect that you can observe dust in situ.
Okay, that's all for me. Thank you.
Thank you.
Thank you. Now, Vladimir Petrovich.
Hello, can you hear me?
Yes.
Okay, first of all, Kristina, I want to congratulate you on such a nicely written thesis. I never read such a simple and concise thesis before. And also I want to congratulate to your family members, because without their support, probably it will not go so easy.
That's true.
So just to say that the importance of this thesis is actually demonstrated by a variety of fields, both scientific and engineering, which are present there. So that's why it's really interesting to me. So my first question is, of course, about that overshot. So I'm kind of a plasma person, so and electronic engineering person. So it is interesting if you could switch to slide 23. Yes. So there is about 20% of electron escape detected events. So, I mean, which are most intensive. So in those cases, do you observe the overshot, or is it somehow related to this population, or for example, to the other 80%?
Not completely. You know, I couldn't find the connection between. I tried, actually, that is a good point. I tried to find connection with the, let's say, the amplitude of the spacecraft and the amplitude of the pre-shoot, of the overshoot, and also the events where I have pre-shoot, do I have the overshoot? And actually, this is one example that it's not true. You see, this
Yes,
a really large pre-shoot, and there is basically no overshoot.
Yes. So when we are
So
there,
I tried to connect all of the things and to realize what's behind, but honestly, I couldn't find final solution,
of course.
except that it is due to that definitely antenna it will take some portion of the cloud.
Okay, I'm sure you will, but it just requires step by step. So about this slide, where you just show the overshoot.
Okay.
Okay, there is, it is really nice because it looks like some kind of inductance is playing a role there. So from the engineering point of view, if you have a resistor, inductor, capacitor circuit, electric circuit, which is present, of course, in the electronics, then you can have such kind of features. So if you have, when you applied the inverse transfer function, you actually eliminated the part of the overshot, which clearly implies that it's part of it is probably due to electronics.
Okay, yeah.
But which is more interesting to me, which could be a kind of possibility, is that the plasma physics is also playing a role there. When you have ions escaping, they will certainly drive some kind of, especially because they're escaping as a kind of shell, as a kind of a bunch of ions. They will probably drive some kind of Whistler wave or instability which is resonant with them. But also all those waves, as you showed on the other slides, for example, I think it was slide 17, as I remember. Yes, so you first have Langmuir modes, electrostatic modes, which were pointed out in previous questions, that referred as electrostatic solitary waves. So it means that they saturate with electrons. They could be driven all the time. So not just only by those bunch of ions escaping, but you have markets with number one, Whistler waves, which are probably driven by ions. So all these waves could contribute by slowing down those ions, or even backscattering them, or even making the population of ions from the plasma being backscattered over the spacecraft. So this could make contribution to this overshot as well, but it really requires to be simulated. So these were just comments. So my question,
I like it.
I'm sorry, I have really a lot of questions, but I would tend to be really short as possible. So the other question, so this is question number 2, is about that oscillation, the correlation of the solar activity. So it's the slide number, let's say 29. Yes.
Okay.
So I agree with some of the previous committee members that, if I heard well, actually in those regions, other than this periodic region, it's not quite true that the signal is random. Even by your eye, you can see some kind of periodicity. So my question about that would be, did you actually apply some other methods for analyzing this signal, for showing what wave modes are really present in this signal? And if not, do you plan to do so? And how would you do that? And then when you answer that to me, I have another last question.
Okay. So no, actually, I didn't apply any other mode except this model that I presented here. But actually, I had the idea that maybe I can use wavelet analysis here, And so in that case, I can actually first have insight in those modulations. So I can see that are there modulations like yearly and or on some larger time scale and so on. So that can be really interesting, because in that case, I can once, for example, when I see this modulation, it will be probably most prominent because it's really obvious. I can try to correlate it with the activity of the sun, and so in that case, I can probably say when this will start. So it's maybe it's not going to start immediately after and it's not maybe it's obviously that it's not going to start immediately after the solar magnetic pole flip, but it will take some time and so on. So really, it should be applied some further analysis on this to make some to answer some questions that are obvious here present. And so I decided definitely that wavelength analysis can be useful for this, and I will try to apply it on the both data set, actually, from wind and from stereo. And so I can be sure that if there is the correlation, I will see it at the both of the satellites. Okay, I could do also for the stereo B, but it's really not useful because it's really short time period. But really, with this analysis, I can find I will probably see those modulations on annually based, and I will see those long-term modulations and so on. So I can definitely distinguish this for that I'm interested in those long-term modulations. I can try to cross correlate with the solar with the modulation of solar activity, and to see when it is happening and what is the start and what is the end, and is it correlating at all, or we just we are maybe wrong.
Well, that's okay. That's a really good point, because it doesn't have to be. If this seems to be correlated with solar minima, it doesn't actually have to be. It could be, as you said, if you can measure some kind of time delay, time shift between the observed data and solar activity, you can practically see if there is a kind of physical explanation for this time delay. So my next question is more like a comment from you. How can we actually interpret those focusing and defocusing processes? Can they be interpreted by multiple physical processes, by different physical processes? I mean, in relation to just what you said, if you have some kind of time delay, if it's really kind of full correlation, so that you really observe such kind of periodic signal appearing right at the solar minima, where we have the magnetic field lines which are oriented. Why I'm asking this is because if you have parallel magnetic field lines, you should expect, so if you have ordered magnetic field, you should expect actually that gravity plays a role there in plasma physics, in the motion of those charged particles. And in those configurations where the solar activity is at its maximum, so the field is more turbulent. So there you could have some kind of diffusive processes. So if you can make just a comment on what could actually be the possible scenarios in these cases.
Okay, I'm not really specialist in it, because
yes,
I just started with basically with taking into account those forces, but I found that Lorentz force is actually playing a really significant role in this interstellar dust flow. So in the situation when the magnetic field lines are pointing southward, basically this will yield to that the magnetic lines will actually push dust toward to the ecliptic plane. And in the opposite, they will actually push them away from the ecliptic plane. So that is what we consider as focusing. So it will push dust it will focus this dust on the ecliptic plane where we can observe it, obviously, and or it will repel it further than the ecliptic plane, and so it means that we cannot observe it. And also that it's probably because if we consider those turbulence of the field, that maybe that they're also favorable at some point to actually to let dust enter the solar system. But I really those are just my assumptions, my thinking about. I'm not sure that that I'm completely right. So it's just
okay. But it's something for the, let's say, future work to include practically, as you said, the gravitationally induced drift in the plasma, and as well as diffusion induced by turbulent field. So that's all from my part. Congratulations once again.
Thank you. So we now move to the so maybe we ask first Ushan Oni. So you may ask your questions or your comments on the chat.
Okay, can you hear me?
yes.
Okay. Well, first of all, I would like to say that it was a great honor and pleasure for me to have the opportunity to collaborate above all with Kristina as well as with Professor Kerim. Kristina really has done a great job, and I can say that she did a very interesting dissertation. Also, presentation was excellent. So I would like to emphasize that what makes this dissertation special is above all that it includes topics from several different fields, such as plasma physics, physics of interplanetary and interstellar matter, as well as knowledge on the instruments and observational techniques. So in that sense, the candidate had to acquire a very broad education. So I would like to congratulate Kristina for a really great job that she has done. Maybe I can ask just one basic question. This is not, I understand it is not the main goal of your dissertation, but in the relevant cases for your dissertation, I just have a question whether interplanetary medium can be treated like dust in plasma models rather than dusty plasma models. I ask this because in the case of dusty plasmas, waves and instabilities can be modified, leading to new waves and instabilities associated with dust. So that can be perhaps analyzed with the mentioned spacecrafts. So I would like to ask you whether you can comment on that, whether it is interesting to do, and of course.
Oh, probably it is interesting. For now, I didn't consider it, but maybe that can be something to think about after. But yeah, we consider actually dust in plasma in this case.
Okay, so I will congratulate. I want to congratulate you finally, and that's all from me.
Thank you.
Okay, Kristina, I would like to congratulate for the book and for all the work you have done. It was not easy during the past 4 years, and as maybe the people didn't know, you have the family in the Prague, and especially the kids, and so you spent some time, several months in Lyon. And then there was the lockdown, the sanitary situation, which doesn't make the life easier for you, but you have shown your great motivation during all the the 4 years. And I would like to point out that in only 1 year, we managed to complete the first author's paper. You made the study on the interstellar brain with twin spacecraft. So then you had to use another instrument because the beginning of the thesis was mainly on stereo. And then you managed to finalize on time your PhD manuscript. So you did a very good work. And I'd like to congratulate you. So, of course, during these 4 years, I was not alone to supervise the work, and Arno did the main part of the job, and he followed day by day meetings in Meudon. So I will let him speak.
Well, thank you, Karine. But I'll be very brief. So first of all, I congratulate you a lot, Kristina, and I think that was very nice to see your presentation today. It was a very good presentation. It was very clear. And I think it generated a very interesting discussion. So it's everybody knows it was great. And basically very happy to see that I know when you arrived at the very beginning, you had no background at all in this field.
Yeah, definitely. Yes.
And to see that in 4 years already managed to make this topic your topic, and that you're happy to talk about it. You talk about it very well, so it's very, very happy. And also, well, yeah, I want to point out that having said that the circumstances was particularly special for first of all, there was COVID and the situation. But you also have a family situation that's not common for PhD students. And yeah, I think your trajectory deserves a lot of respect.
Okay, thank you.
I will ask one question. You have shown 3 cases of observations in young rays. Dust, in fact, plasma wave around the local frequency. But I understand, I'm not a specialist, that you observe only one brain impact at a time.
Yes.
Don't you ever observe superimposed impact?
Yes, sometimes you have some spikes around that are related to the nanodust, but basically what we were interested were just in those spikes that are simultaneously prominent on all 3 antennas. So we just include those. No, they can be around, but usually the amplitude is much smaller than for those small spikes around that refer to the nanodust. And so we just okay, we have plots like that. Of course, we have it shouldn't be like this perfect. This is one of the examples. It can be some fluctuations before and after, but basically in the for stereo, in the middle of the snapshot, it should be the most prominent event, and in our case, that event should be dust.
Okay, so now we have this deliberation. So we stay here.
So
we stay here. So I will ask you to go on the
symétrique par rapport à l'extension. J'ai cru comprendre, oui. C'est bien, j'ai d'autres questions, mais tu as posé toutes celles que j'avais proposées, je vais les garder en réserve.